Let's take a look now at the addition, subtraction, the multiplication, and division properties of equality. We're going to begin with a couple of definitions. First, let's define an equation. An equation is what you get when you take two expressions and state that those two expressions are equal to each other. They may look different, but they have the same value. So an equation is a statement that declares two expressions, algebraic expressions, are equal to each other. Okay. So examples of equations can be things like x equals to 5. That's a expression, and so is that. They're both very simple expressions, and we stated that they are equal to each other. Now, these can be made more complicated. We could say something like 2x plus 5 is equal to 30. And again, that is an expression. That is another expression, and we can say those are equal to each other. We can make those even more complicated. We can say something like 3x minus 9 is equal to 2x plus 12. And again, that's an expression. That's another expression, and they are set equal to each other. Now, keep in mind that variables have different values. You can take on any. Well, see, the thing is, you can substitute anything you like for x. The problem is that most of the time, it's going to give you a nonsensical statement. For example, right here, I could say x is equal to 10. In fact, I just did. I said x is equal to 10. The problem is that if I do that, I can say 2 times 10 is 20, plus 5 is, no, it's not 30. Huh? 20 plus 5 is not 30. In fact, I could say lots of numbers. I could say x is equal to 1. I could say x is equal to 25. I could say x is equal to 100. But none of those are going to make this statement true. So whenever you talk about an equation, the statement that declares these to be equal to each other doesn't have to be true. There are true equations and there are false equations. So here, note there are true equations. For example, 2 plus 3 is equal to 5. That's an expression. And that's an expression. And I've stated they're equal to each other. And it's true, they are equal to each other. And there are false equations. For example, 2 plus 3 is equal to 916,412. That is definitely not true, right? That is a false equation. So an equation is simply a statement. It doesn't have to be true or false as long as it's a statement where one expression is set equal to another. But obviously, a false equation is probably not something we want. Generally, we want true equations. Now, when you have all constants, it's easy enough to confirm, yes, it's true, or no, it's not true. But what about with variables? How can we confirm whether or not our equation is true? For example, here, we don't even know what x is. We just know that it's a number, it's a real number, but otherwise we have no idea what x is. So how can we confirm whether or not this is true? Well, that's what this section is about. Here we're going to look at solving equations and what it takes to do that. But before we can do that, we want to talk about what does it mean to solve? What does it mean to have a solution? The word solve in everyday language means to find an answer. In math, it's a little more specific. Here, 2 plus 3 equals to what? Oh, it's equal to 5. Oh, so then that's your solution, right? No, it's not. That's your result. That's your answer. A solution is not just any answer that you get in a math question. It's a very specific kind of answer. Okay, so what is it? A solution to an equation is a number or set of numbers. It's possible you can have more than one. that when substituted for the variable or variables, again, there can be more than one, gives a true equation. So, as I mentioned before, I could say x is anything. I could say x is 10. I could say x is 100. I could say x is lots of things. But for the most part, whatever I say x is going to give me a false statement. It's going to give me a false equation. Here, for example, if I say x is 100, 100 times 2 is 200. 200 plus 5 is 30. Yeah, no, it's not. That's false. Here, 2 times 100 is 200, plus 5 is 205. And we're saying 205 is equal to 30. Of course not. That's false. In fact, most numbers that we plug in here would give us a false statement. 2 times 20 is 40, plus 5 is 45. 45 equals to 30. Yeah, that's not true either. That's false. And in fact, if you picked 100 numbers, chances are all of them would give you a false statement if you plug them in right here. However, notice what happens if I plug in the number 12.5. Or I could say 12 and a half, or any way I want to say it. I'm going to say 12.5 for now. Well, let's see. Order of operations, I multiply first. So 12.5 times 2 is 25. 25 plus 5 is 30. And notice, plugging in most numbers gives me a false statement, but that number in particular gives me a true equation. Because of that, we can say that 12.5 is a solution to this equation. Now, notice I said a solution. We rarely ever say the solution because many equations can have more than one solution. So a solution. It can be one or more. Now, again, there will be some equations that do only have one solution. So here we will say 12.5 is a solution to the equation 2x plus 5 equals to 30. Note that, again, there may be more than one solution. Because of that, we often write solutions, whatever solutions we find, in what's called the solution set. So note all solutions to an equation form a solution set. That's the name. It's called a solution set. And the way we write it is, which uses curling braces, which is denoted meaning this is the way we write it. It's denoted between braces. So here, 12.5 is the only solution to this equation. So here we could say the solution set to the equation 2x plus 5 equals 30 is you're going to put all of your solutions in between these braces. Now, when you only have one solution, your solution set really just looks like here's your solution with these symbols around it. However, as you go into more and more complicated equations, you'll start having lists of solutions. So here you'll have a list of numbers. And if the equations become complicated enough, we actually start using different ways of writing this out rather than just a list. All right? So here, this is just an introduction to this material and an introduction to this notation. For now, it pretty much looks like, okay, with the braces or without, it wouldn't really make any difference. And for now, that's true. But as you move into more complicated material, you'll be introduced to reasons why the set notation by using the braces can be very convenient. All right? So your solution is a number or set of numbers that, when substituted into the variable, make this a true equation. Right? And if you take every solution, if there's only one, okay, well, there's only one. If there's 10 of them, when you list all 10 of them between braces, that's called a solution set. All right, now, you might look back at this equation and say, well, okay, fine. I can tell you're right. If I plug in 12.5 right here, 12.5 times 2, that's 25. 25 plus 5 is 30. Okay, yeah, that's true. But how did you find that number in the first place? Did you just guess? No, I didn't just guess. Okay, well then, how are we supposed to find that? I mean, okay, yeah, maybe this answer's, maybe you could guess at this answer. This isn't that hard of an answer to find, I think, right? These numbers aren't very big. You could guess and check a little bit, and eventually you'd get an answer. That is a terrible idea once your numbers start to get bigger, or once your expression starts to become more complicated. Here, this expression was fairly simple, 2x plus 5. What if it was 2/3 x minus 1/3 raised to the second power? Here you have 30. What if it was 30x minus 1/8? Guessing solutions is generally not a good idea because, well, note that your solution can possibly be any number. X can represent any real number. To find the one that makes this equation true, you would have to go through, well, every number, or at least thousands upon thousands of potential answers. So guessing and checking is not a good way to do this, not a good strategy. Instead, what we want to do is we want to rely on what are called the properties of equality. Right? So that's what this section is mostly about. So let's talk about what we're going to be solving. You say, well, we're going to be solving equations, right? Well, yes, but for now, we're going to stick with a very particular kind of equation. There are lots of different kinds of equations. Definition. We're going to be sticking to linear equations in one variable. You say, what is that? Well, let's see. Let's define this. We're going to take three numbers. We're going to let A, B, and C be real numbers. Doesn't matter what they are, just as long as they're real numbers. Now, we want to make sure that A is not 0. We'll see why in just a second. B and C have no restrictions. So let A, B, and C be real numbers such that A is not equal to 0. Okay? We're going to let X be a variable. So it is also a number, but we don't know what it is. It's not constant. Here, these are constants. Let X be a variable. And we don't have to use X. You can use any symbol you like, but X is pretty common. You could use Y or Z or P or Q or whatever you like. But X is common enough. We're going to go ahead and use that. All right, so you have three real numbers, making sure that this one's not 0, and you have some variable, whatever you want to call it. A linear equation in one variable, and that's what we're defining. We're defining a linear equation in one variable, is an equation that can be written in the form AX plus B is equal to C. All right, so here we said we want to make sure A is not equal to 0. That's because if you have A is equal to 0, then 0 times X would be 0x, meaning there's no X here. We want to have a variable in the problem, hence the name, a linear equation in one variable. And since we want to make sure that there's a variable in that equation, we can't multiply it by 0, because otherwise that means it would go away. All right, so linear, for now, that's just a name. It's going to take a little more meaning. It's going to take on a little more meaning later on down the line when we start looking at graphs. To spoil a little of the surprise, it has to do with the shape of the graph. Equations that have this form are called linear equations because their graphs are lines. All right? We'll talk about that in more detail later on down the line. The other thing here is notice that you have a single word here that it needs to be elaborated on, it can be written in the form. Remember that expressions do not always start off in a simplified form. Sometimes you have to simplify by combining like terms, distributing, or using the associative or commutative properties to rewrite things in a neater fashion. What this means is your equation may not have started off this way, but after you finish simplifying, it'll end up like this. Right? Examples of linear equations in one variable include things like, well, the one we just saw, 2x plus 5 equals 30. 2x plus 5 equals 30. Here, a is equal to 2, b is equal to 5, and c is equal to 30. Note that a, b, and c can be any real numbers as long as a is not 0. If we like, we can have the other ones be 0. We can have 2x plus 0 equals 0. That's a perfectly acceptable linear equation in one variable. We can say these are fractions or decimals or anything else. We can say 1.3x minus 7.92 equals 8.35. We could say 1/8 x plus 5/6 is equal to negative 1/15, like that. And all of these are perfectly acceptable linear equations in a single variable, in one variable. And even if it doesn't have this form to begin with, as long as it can be rewritten in this form, for example, if you have 2 times 3x minus 5 plus 1 is equal to 9, that is also a linear equation in one variable. Because here you could distribute the 2. 2 times 3x would give us 6x. 2 times negative 5 is negative 10. Like that. And then you could always combine your like terms. Negative 10 plus 1 would give us negative 9. Just like that. Okay. You might notice that I'm using a symbol here, a little arrow. That's because here the equal sign is already used as part of your equation. So whenever you are simplifying expressions like 2 plus 3 minus 15, you would say, okay, that's equal to, okay, do those first. That's 5. And then 5 minus 15 is negative 10. Here, the equal sign is used to link together these expressions. You're saying this is equal to this is equal to this. But here the equal sign is already part of this expression. So you wouldn't say this equals this is equal to this equals this is equal to this equals this. The equal sign is already being used for the purpose of expressing the equation. So here we use another symbol. We can use an arrow here to say, okay, that line leads to this line, leads to this line. Or it's common enough not to write anything here. You don't have to use a symbol. You'll notice that you can just say this and then write the next line and write the next line. The reason I often write the arrows is because it helps to show that, okay, I'm not done with the problem. This led to this one, led to this one. Without the arrows, this is a problem, this is a separate problem, this is a separate problem, and this is a separate problem. But it really is just a matter of taste, which way you prefer to do it. You'll often see that if I go from one line of an equation to another, I'll put an arrow required. You don't really have to do that. All right, so what we're going to be doing is we're going to be looking at solving equations that are of this nature. We're going to be looking at solving linear equations in one variable. We're going to be looking to, and again, when we say solve, we mean to find the solution. We mean find the number or numbers that when you plug them in, you're going to get a true statement. Okay? So how are we going to do that? Well, we're going to use the following properties. We're going to begin with some algebraic expressions. So here, this is the addition. So these are the properties of equality. There are 4 of them, but they're very closely related. So here I'm going to write them all together. They are technically separate, but they're so closely related and so similar to each other, there's not really any problem just stating them all at once. So let's begin with 3 different algebraic expressions. Let A, C be algebraic expressions. Okay. If A is equal to B, then A plus C is equal to B plus C. This is called the additive property of equality. The addition property. Of equality. I already called at the very beginning of the section, I called it the addition property. I don't want to suddenly change the name. Additive property would be fine, but I don't want to change the name all of a sudden. I want to be consistent. So here, what this says is, if you have two things that are equal to each other, if you add something to one of them, and you add the exact same amount to the other one, well, then they're still equal. For illustrative purposes, consider the following. It's 25 cents. Okay? Here is another 25 cents. Okay? All right, now these may not look the same. That's a single coin. That's 3 coins. But they are equal. They have the same value. So here you have an A, and here you have a B. They look different, A versus B, but they are equal. All right, 25 cents, 25 cents. Now, let's say I add something to this stack, a single penny. Well, now those are not equal anymore. Oh, but they will be equal as long as I do the same thing to both stacks. So if two things are equal to each other, regardless of whether or not they look alike, and I could have started with 2 quarters, like that, and those do look alike. Or I could start with a quarter and over here 2 dimes and a nickel, and these don't look alike, but they're still equal. And if two things are equal to each other, as long as I add something to one of them, as long as I add the same amount to the other one, they're still going to be equal. That's all the addition property says. If you add something to one, as long as you do the exact same addition to the other one, your 2 stacks are still the same. They're still equal to each other. Okay? Now, a very similar related property states something almost exactly the same. If you have A is equal to B, then A minus C is equal to B minus C. Same idea. If you start off with 2 stacks that are the same, whether or not they look the same, here these are the same, they're both worth 26 cents. If I subtract something from one of them, well, they're not equal anymore. Oh, but if I start off with 2 stacks that are the same, if I subtract the same thing from both of them, if I take the same amount away from both, well then what's left is still the same, 25 versus 25. Right? So it's the exact opposite of the addition property. The addition property says if I have 2 things that are equal and I add the same to both, that stack is still equal to that stack. If I have 2 stacks that are the same and I subtract the same from both, well then both stacks are still the same. Okay? So this is, it doesn't take much imagination to realize, this is called the subtraction property of equality. We'll see some examples here in just a moment. Let's continue on to the next property. Let's say you have A is equal to B. Well then, multiplying A times some number and multiplying B by that same number still gives a valid equation. Again, for illustration purposes, let's say you start off with 2 stacks that are exactly the same. And again, maybe they look the same or maybe they don't. It doesn't really matter. So here, let me start with this one right here. Okay, so here you have a stack A, 25 cents, and here's another stack B, which is also 25 cents. They don't look alike, but they are equal. Now let me go ahead and multiply both of them by the same amount. Here, let me multiply both of them by 2. Let me double their amounts. Okay, well that's now 50 cents, and So is that one. So they started off the same. They both started off as 25 cents. Now if I multiply both of them by 2, well, now 25 cents becomes 50 cents. And as long as I do the same thing to the other one, double its value, same thing, 50 cents compared to 50 cents. And if instead of doubling, I was tripling, if I was starting off with, okay, 25 cents versus 25 cents, now I'm going to multiply this by 3, well, that's going to give me 75 cents. Okay, well, those aren't equal. Oh, but if I do the same thing to the other one, if I triple its value, multiply it by 3, that will also be 75 cents. And even though they look a little different, they are still all equal. Okay? So this is called the multiplication property of equality. And it takes no imagination to see what the last one has to be. It's got to be division. If A is equal to B, then A divided by C is equal to B divided by C. Here there is one extra thing we have to state. Here you can't let C equal to 0 for this one, because again, division by 0 is undefined. So this is the only one where you need an extra stipulation, where C is not equal to 0. You can divide by any other number. It's fine, just not 0. And this one's called the division property of equality. Okay. Essentially, all of the properties of equality can be summed up by saying, if you have an equation, as long as you do the same thing on one side as you do to the other, you still have a valid equation. Whether that something be adding or subtracting or multiplying or dividing doesn't really matter. If you start off with a true equation, as long as you do the same thing on one side as you do to the other, you'll still have a true equation. So let's take a look at some examples of using these. Let's consider some equations, and we'll see how we can use these properties to solve those equations. We're going to start off with dealing with these properties only one at a time, and then we'll see that they can actually be combined so that you can solve more complicated equations. But for now, let's deal with them one at a time. Let's say you have an equation that looks like this. X plus 3 is equal to 9. Okay? Now, yeah, I know the answer is 6. And you know the answer is 6. And if you didn't, well, now you do, right? But the point of this example is not to get the solution. Here, the answer is fairly obvious. I have some number plus 3 is equal to 9. Yeah, it's going to be 6. Here what I want to do is I want to illustrate the technique. I want to illustrate what it looks like to use these principles to solve an equation. Because in just a second, the numbers won't be so nice. So what we want to do is we want to figure out what x is. If in the end my equation looked like x equals to 6, for example, is what I want to get, then I would have my answer. X is 6. So what I want is I want to get that x by itself. I want to have x equals to whatever it's equal to. All right, so that means that extra plus 3 is in my way. I don't want to know what x plus 3 is. I want to know just what x is. So what I want to do is I want to subtract 3. That way, that positive 3 and that negative 3, these are additive inverses. When I combine them, they're going to give me 0. But if I'm changing one side of an equation, the only way to maintain that equation is to do the same thing on the other side. So if I subtract 3 to get rid of that 3, I need to do the same thing on the other side. And that's going to give me x is equal to, right, this is gone, so we can write x plus 0, but generally we don't. We just write x. Here 9 minus 3 would give us 6. And this is our solution. And of course, you can always check. If ever you have a solution, what you mean is, I have a number that if I plug it in, it's going to make this equation equal to 9. So if you're not sure if you did it right, you can always just plug it in. 6 plus 3 is 9. Yeah, that works. Now, if your numbers are not very nice, this will still work. So here, this one, with whole numbers, you can probably just guess and you get the answer, right? You can count and get the answer, right? You say, okay, 3 plus something is equal to 9. You can just start counting. 4, 5, 6, 7, 8, 9. Oh, okay, there we go. It took me 6. But if your number was something like x plus 3/8 is equal to negative 5/12, well, then guessing the answer might be a little hard. And if you can count by fractions, well, you've got to show me that skill, because that's not something I know how to do, right? But it doesn't matter that these numbers are not as nice as these. We know how to solve. Because what we want to do is we want to get that x by itself. We want to have x equals whatever x is equal to. We want x equals the solution. So that means that 3/8 is in the way. We want to get rid of it. And to do that, we're going to subtract 3/8. 3/8 minus 3/8 is 0. That goes away. But whatever I did on one side, I need to do the same thing on the other side. That's minus 3/8 there as well. So now over here, that x is now by itself is equal to. So now I have to subtract these. Okay, well, I need a common denominator. Let's go ahead and do this off to the side over here. If I take negative 5/12 minus 3/8, let's see here. That's going to be minus 5 over 2 times 2 times 3, minus 3 over 2. To give this a common denominator, I need to multiply this top and bottom by 2, and this one by 3. Negative 10 over 24, and here that's minus 9, also over 24. 2 times 2 is 4, times 2 is 8, times 3 is 24. And now you can combine those. Negative 10 minus 9, that's the same as saying negative 10 plus negative 9. You add numbers, and since they're both negative, your answer is also negative. So here that's going to be negative 19 over that common denominator, which might have been a little hard to guess, but we don't need to guess. There's our result. This is our solution. This is an example of the subtraction property, because notice, what did I do? I subtracted the same thing on both sides. I subtracted 3 and I subtracted 3. The addition property works pretty much the same way, except I'm using it by adding on both sides. So as an example of that, let's say I have x minus 7 is equal to negative 4. Okay. Well, I don't want x minus 7. I just want to know what x is, which means that minus 7 needs to be gotten rid of. Okay, so we'll do that by adding 7 to both sides of our equation. And again, whatever you do to one side, you do to the other side. This isolates the x. It does what now? Isolates. That's the language we're going to be using here. We want to isolate the variable. When we say isolate, we mean we want to get it by itself, which is what we've done here. We've got x by itself equals something. X equals something. When we say isolate the variable, that means by the time you're done, you need x, or whatever variable you have, y or z. You want the variable by itself equals to the solution would be on the other side. Here we have 7 minus 4, and that gives us 3. And that's our solution. We've solved the equation. And of course, if our numbers are less nice, well, then it doesn't change anything. We do it the same way. We can say something like x minus 7/15 is equal to negative, let's see here. Let's say negative 4/9. So in fact, go ahead and give that a try. Go ahead and pause the video, go through, and see if you can't solve this equation, solve for x. Once you're done, go ahead and unpause, and we'll go through it together. All right, so here we want to get rid of that minus 7/15, which we'll do by adding 7/15. But whatever you do to one side, you got to do on the other side. So here, this is gone. 7/15 minus 7/15 is 0. If you want to write x plus 0, that's fine, but most people would just write x. Here we need to put these together. Let's do this off to the side. If I take negative 4/9, plus 7 over 15. That's negative 4 over 3 times 3. And that's plus 7 over 3 times 5. And now to make these denominators the same, I need to multiply here by 5. And I go and do the same thing on top. And I need to multiply this by 3. And I'll do the same thing on top, times 3. So this fraction has now become negative 20 over 3 times 3 is 9. 9 times 5 is 45. Plus, and that's going to be 21 over 45. And of course, now that you have a common denominator, you can go ahead and add those. You have 21 plus a negative 20, which is really just 21 minus 20. This is just the number 1. Over your common denominator of 45. And there we go. That's the solution to that equation. Let's look now at some examples of using multiplication and division with the restriction in mind that division by 0 is not allowed. Yeah? So for example, let's say we have three x is equal to 75. Well, again, we don't want 3 times x, we just want x. In every case, we're trying to isolate our variable. So to get rid of this multiplication by 3, we can divide both sides by 3. 3 divided by 3 is the number 1, which is what we want. We want 1x. On the other side, 75 divided by 3 will give us 25. And that's our solution. And of course, you can always check these. We substitute this back in. You say x is 25. 3 times 25 is, in fact, 75. If you're dealing with a fraction, keep in mind that dividing by a fraction is the same as multiplying by a reciprocal, which means you can do that in 2 parts or just in 1. So, for example, let's say we have 3 fifths x. 3 fifths x is equal to 9. Let's say, for example. All right, now, we can say dividing both sides by 3 fifths is what we need to do, and that's perfectly fine. But remember, when you divide by a fraction, that's the same as multiplying by a reciprocal. So you can first say, let me divide both sides by 3 fifths, and then let me change that division into multiplication. But since we know for a fact that's what's going to happen, because it's the only way we can divide fractions, we might just jump directly to that second step and saying, yeah, I know I need to divide by 3 fifths, but the way I'm going to do that is by multiplying by 5 thirds. Notice that this is still perfectly valid because the division property is also joined by the multiplication property. It doesn't matter if you multiply or divide, as long as whatever you do to one side, you do to the other side. Notice here, 15 over 15, that's the number 1. Which is what we want. We want the number 1 times x, 1x. On the other side, we can go ahead and divide this out. Note that that's going to be 9 is the same as saying 9 over 1. Here we can simplify that out. 9 is 3 times 3. And then all the rest of these numbers are prime numbers. So here this 3 divides into that 3. And so we're left with 5 times 3 is 15 over 1. And 15 over 1 is perfectly valid. However, most people would just write that as a whole number. Most people would just write that as 15. Either one's fine. If you write 15 over 1, that's okay. Just 15, that's fine too. So here you see an example of division. And here, this is technically division. We divide both sides to get rid of this coefficient. But the way you divide a fraction is by multiplying by its reciprocal. So this is a little ambiguous. I'm not really sure if we kind of use the division property, but we also kind of use the multiplication property. It doesn't really matter though, because regardless of what you want to label it, it works the same way. As long as you do the same thing on both sides, you can isolate your variable and get your result. So go ahead and give this a try. go ahead and isolate your variable. Let's have you try 2.5x. So you have a decimal. 2.5x is equal to 9.25. Okay. And then we have one with decimals. Also try one with fractions. Let's have you try, let's say 5/8. 5/8 x is equal to, let's say 5/12. Right. Give both of those a try. Go ahead and pause the video, and once you have a result, go ahead and unpause and we'll go through it together. All right, here, these are being multiplied. We don't want 2.5 times x though, we just want the x. So we can divide both sides by 2.5, and that'll isolate our x. So x equals to, well, we need to do this division. So let's go ahead and do this over, let's go ahead and do this down here. Whenever you're dividing, if the numerator has a decimal, no problem. But if the denominator has a decimal, that can be complicated. So what we want to do first is I'm going to go ahead and multiply top and bottom by 10. That way, if I multiply by 10, it's going to move the decimal over one space. And whatever I do on the bottom, I did on top, move that over one space. So here, that's going to be 92.5 over 25. Okay. But now we can actually divide that. Okay, so let's go ahead and do that. Let's see, I think we can do this off on the side here. 92.5 divided by 25. Okay, 25 goes into 92 3 times, because 4 times would be too big. 4 times 25 would be 100. 3 times 25 is 75. And if you take 92 minus 75, that'll give us 17. And then you take your 5, bring it on down. Okay. So now 25 goes into 175, it looks like 7 times. 7 times 25 will give us 175. Subtract, and you have no remainder. So here you end up with 3.7. So that's our solution. X is equal to 3.7, which again gives us a good reason why we want to be able to use these properties, because here guessing at that answer would have taken a while. Okay. Same thing with the fractions here. I can go ahead and divide both sides by 5/8. Now remember, we can say divide by 5/8, divide by 5/8, and then remember that dividing by a fraction is the same as multiplying by a reciprocal. But since we know that's what's going to happen anyway, we might be saving just a bit of time if we just go ahead and jump directly to that. Okay. So here we go. We're going to go ahead and multiply both sides by the reciprocal of this fraction, because here 8 times 5 is 40, 8 times 5 is 40. Hey, 40 over 40, that's just the number 1. That's what I want. I want 1x. So 1x is equal to, here let's see if we can't simplify. 5 is already a prime number. 8 is 2 times 2 times 2. 12 is 2 times 2 times 3. And 5 is just the number 5. And here you note that almost everything divides out. Here, when you multiply the two fractions together, it joins them together as one big fraction. And so now, let's see here. Those 2's divide, and so do those 2's. And these 5's divide as well. So here, that's 1 times 1 times 1. That's all 1 times 2 is the number 2. On the bottom, 1 times 1 times 1. That's all 1 times the number 3. So if you take 5/8 x is equal to 5/12, it turns out that your variable must be 2/3. That's your solution. And remember the language for that. A solution is a number that, if substituted in for the variable, makes this statement true. Here I could plug in any number I wanted. I could say x is equal to 9. I could say x is equal to negative 17. I could say x is equal to anything. But if I multiplied those numbers by 5/8, I would not get 5/12. But 2/3 is the correct number to use. So that if I multiply 5/8 times 2/3, that will give me 5/12. That'll give me a true equation. Finally, we come to talking about solving of equations where your statement is not given symbolically, it's given in words. Just like we have sum meaning addition, and product meaning multiplication, and difference meaning subtraction, and quotient meaning division, we have a word for the equal sign, and that's the word is. So in a statement, anytime you see the word is, that means equals. Now, there is one exception, and that's when, or I guess two exceptions, and that's when the word is followed immediately by greater than or less than. If you say is less than, now remember the phrase less than by itself means subtraction, but is less than, that's an inequality. Here we're dealing with only equations, but do keep in mind that this is an exception to this statement here. Is means equals. Is less than means, well, is less than. It's this one right here. And if you say is greater than, that means this inequality. So here we're not really worried about inequalities in this section. It's we're only worried about this, but this is the exception to saying is means equals. So just keep those in mind. All right. So let's say we have a statement. Let's say half of a number is 4. Okay. Now, here, whenever you see a phrase like a number or some number, that's where your variable goes, because it is a number, but you don't know what that number is. It could be anything, hypothetically. So this is where your variable goes. Okay. So half of a number means half of a variable. X is a common variable, although you're free to choose whatever letter you like. You can use any letter that you care to use. However, X, Y, and Z are probably the most common variables that we have in algebra. So here, half of a number, that's going to be half of X, is, that's where your equal sign goes, 4. So there we go. Of course, here you can always go ahead and multiply both sides by 2. That way 2 times a half, that's 2 halves, which is just the number 1, that's gone, right? 2 halves is the number 1. But whatever I do to one side, I do on the other side. So here that's going to be, that goes away, gives you just 1x. Here, 4 times 2 will give us 8. So half of a number is 4. Oh, that number must be 8. Go ahead and give that a try. You're gonna first write this in symbols, and then you're gonna solve. In fact, let's go ahead and let's just go ahead and say that, solve. Oh, let's see. Let's say 2 ninths from a number is 1/8. And yes, I did just forget how to spell 8. I'm missing an H there, right? H-T-H. There we go. E-I-G-H-T-H. There we go. All right. So go ahead and give that a try. Go ahead and we're going to turn this into a statement using symbols, and then you're going to solve. Go ahead and give that a try. Pause the video, and once you are done, go ahead and unpause, and we'll finish that off together. All right, so let's take a look here. You're going to take 2 ninths. Well, that's a fraction. 2 ninths. 2 over 9. From a number. Now remember, from means you're subtracting. Now, you're subtracting from a number. That means that that number is what you started with, and you're taking 2/9 away from that. So the 2/9 is what's being subtracted. A number, again, that's your variable, so that's going to be an X or a Y or a Z. If you use a different letter here, that doesn't change anything. If you use W, that's going to give you the same solution. So 2/9 subtracted from a number. So you started with that some number, and then you took away 2/9. That is, it's going to give you 1/8. 1/8. So now you can solve that by adding that 2/9 to both sides. Here, negative 2/9 plus 2/9, that's just going to give us 0. This is what we want. We don't want anything being added or subtracted here. We just want the X. Over here, we want to go ahead and add these two together. That's going to be 1/8 plus 2/9. Let me go ahead and give these a common denominator. 8 is 2 times 2 times 2. And 9 is 3 times 3. Right, so it looks like the common denominator is just the product of the two, right? Whenever they have nothing in common, then the common denominator really is just you're multiplying everything from one side to the other. So here that's going to be 8 times 9. That's 72. That's your common denominator. Your numerator, 3 times 3 is 9, plus times 1 more is still 9. Plus, and again over here that's 72, right? That's 9 times 8, that's 72. 2 times 2 is 4, times 2 is 8, times 2 more is 16. And so when we add these together, we get 16 over 72 plus 9 over 72. 16 plus 9, that'll give us 25 over 72. And that is our result. Now you notice that we have been dealing with all of these operations just one at a time. We've only been using one property at a time. Here we use the addition property. Here we use the multiplication property. Here we use the division property, right? Here we use it again. So that is the end of our section here. That is the end of our topic for now. But coming up soon, we're going to have to talk about how to combine these. What happens if you need to use 2 or more of these properties simultaneously? Can that be done? Yes, it can. How do we do it? Well, we'll talk about that in a coming section. But for now, that is it for the topic at hand. If anybody has any questions, comments, or problems, please make a note of those and reach out. And I hope you all have a nice day.